So now let's start developing a 1D mesh in gmsh. So gmsh is a free software which is really fantastic for meshing finite elements, higher order finite elements as well. You can mesh quads and you can do so many things. It's an open source tool, so the source code is also available. I have provided a download link for gmsh, and you can just download it and start it. And let's build a 1D case again for our test case, a 1D mesh, and then let's go to 2D and 3D. So the process is really simple. So I'll use a GUI, but you can also use the script. So first we have to create the script, or the file. So this file extension is a geo extension. So now you just have to press file, new, and let's just define a file called as line.geo. So let's just use open cascade. Okay, so now we just have to start defining our line. So first we go into the geometry and the elementary entities, and we go into add, and let's just add a point first. So remember, our mesh is just the same one as before. I'm talking about the geometry, I'm sorry. So it is the same geometry as before, which is running from 1 to 12. So I've added these 2 points. So we are modeling the same problem. Okay, so now let's construct a line between both of them. So we'll just press Q so that we don't add. So Q is for getting out of any function that you are using, any functionality you are using here, and E is for selection. So let's just create a line by selecting these 2 points. And okay, so the line is selected. Now let's go to physical groups, and this is for distinguishing the boundaries from the interior nodes, right? Or even if you want to set an interior boundary, or you want to set basically 2 different domains at these interior points, right? So this really allows us to distinguish between all of these different parts of our geometry. So in this case, let us just click on point and press E. So this is one physical group. So this is for your interior boundary, which is set at 1, and the exterior boundary is this one. So we define a second physical group for that. And then we have no more points left at the boundary. So now we just click on curve. So this is our interior. Press E and select. So this has been assigned a physical curve. So this is 4, and you can see this if you just open the edit script. So you can see the script here. So the curve has been labeled as 4, the points have been labeled as 2 and 3. Okay, so now we can actually do the meshing, and then we'll start seeing how this works. So here I just press 1D and I have got this 1D mesh. So I just have 3 points here, and there are 3 nodes here. So let's go to tools, options, and let's look at the mesh. So here you can see that the label type is set to physical groups. So these are the 3 physical groups that we tagged, but we can also set it to nodes or element tag. Now I can see that there are these 3 nodes, and you can see that they are not in a straightforward order. That is because we are using gmesh. So it is made for unstructured grids. So it is not going to use a straight order. So the element to node connectivity is going to be important. So here we just have 2 elements, right? 2 linear elements. And if I put set order as 2, I'm sorry. So, right. So you can see that there are 2 more points here inside these 2 elements. If I put set order as 3, I get basically 4 points per element, right? 2 interior points. And you can see that the order is just scrambled, right? So the element to node connectivity is really important here. Okay, so now let's just refine this geometry. Let's set order as 1. Let's refine this geometry by splitting, and now you have got a lot of nodes here. Let's switch to the physical groups again, and you can see that all the interior nodes are 4 and the boundary nodes are 2 or 3. Okay, so the inner boundary is 2 and outer boundary is 3. Okay, so now let's export this. So the standard way of exporting this is probably into .msh file, and in Python you have a reader for this directly, but in MATLAB I was not able to find a reader, so I just built a reader by myself. And in Julia also I am using the same reader, which I so I just export it again using the MATLAB format. And this is really you could open it in any language, because you can open it in a notepad as well. And so you can even use this MATLAB format or .msh format for reading in Julia or any other language. So really the format doesn't matter. So here let's use MATLAB format, line.m. Okay, so let's export this as line.m, and now let's see how it looks. So this is your line.m, and now you can see here these are the total number of nodes. These are your node coordinates. You can see that they are scrambled. They are not necessarily in the ascending order. And these are your elements. So your first element is 1, 3, and the last column refers to your flag. Okay, so this is the flag is basically this 4 flag, which shows that it is the interior. Let's select node, and so now you can see the first element is just 1, 3, second element is 3, 4, and so on. So you can just see 1, 3, 3, 4, 4, 5, and so on. So this third column really allows us to distinguish it from the boundary. And these are your boundary points 1 and 2. So this is your boundary at node 1. So you have flag 2, right, at node 1, and here you have flag 3 at node 2. Okay. So that is what you're seeing here, and you can use flag 2 or flag 3 to distinguish both of them. So so now that we have understood this, so also let's do this for a quadratic mesh. Okay, and I will export this again as line q.m. Let me open this as well. So now you can see that you have lines 3. Here you just had lines. Instead of that, you just have lines 3. So you just have to read that. I mean, while developing the mesh reader, you just have to tell it if it is order 2 mesh, it will be lines 3. Okay, and so you have basically 3 dots here, the 3 points for every element, and you have this 4 flag. But now let's look at the ordering of these nodes. So the first element is this 1, 3, and 34. 34 is in the middle, but gmsh is reading it in this order. So it is counting the edge nodes first and then it is counting the mid node. Okay, I'm sorry. So really we have to be careful while assigning our shape functions. So if we look at our shape functions in our original file, so for quadratics we had these kind of shape functions, and this guy was in the middle exactly. It goes to 1 at the mid node at 0.5. So this guy has to be at the end. Okay, if we are using gmesh, and same for dn dxi as well. So long as we do that, our shape functions will remain continuous. Otherwise they will be discontinuous and we'll get blow-ups at the boundaries, because we are calculating the derivatives of those discontinuities. So long as we pay attention to that, I think this is all that we have to learn right now. So let's just do this in MATLAB. Let's look at the mesh reader file. So this is the read mesh file which I have just developed in MATLAB, and you could just pass this mesh file into AI, and it will also give you something very similar. So really we are just going to develop a struct. In case of Python or Julia, you could call it a dictionary. So this struct is in the form of node info, element info, and boundary info. So let's just read this. So the file, you really don't have to, we have already talked about the logic. There is nothing related to finite elements here, so we don't have to go into depth. You can just read this file. It's pretty straightforward. So you are just reading lines when you have case 1 and order 1. So you just put a input of order here. If order is 1, it asks for lines. If order is 2, it looks for lines 3, and that's how it's just parsing through the file and reading it. Okay, so this is just a plug and play file which I'll be providing. So you can just use it as is. So let's look at the struct. Okay, so now let's read mesh line dot m comma 1. Okay, so this will give us the struct. So if we double click on element info, so you have elements inside it, and these are your elements, your linear elements. These are your boundary elements, so these are all of your boundary nodes, and this is flag 2. So when I say flag 2, it will select all the nodes for flag 2. So here there is just 1 point in flag 2, 1 point in flag 3, and so on. So this is your structure, and this is your node info. In node info, if we go into X, we'll find all of this. So these are your radial coordinates. So now this structure is very simple, and it allows us to directly modify our original file. So let's just solve our same test case now, just by using the gmsh files which we have just created. So I'll just save another file here, live1d underscore gmesh .m. Okay, so we don't have to touch the test case or anything in the weak form or the isoparametric mapping. Let me just remove this L1 error. So that process is going to be the same, so you can just ignore that. So really we just have to modify the mesh and connectivity, and we have to modify the shape functions. So let's do that. Let's start off by first calling our mesh reader. So let's call our mesh reader first for our linear elements, and so we need n element, we need r as well, and we need lm as well. So let's just look at this again. So these are your elements, so you just have to write. So let's build lm first. Lm is equal to, this is the list of elements, so you can write it as lm info dot elements. So this is your lm. For r, you just have node info dot x, right? So node info dot, right, so node info dot x. And for nlm, we'll just consider lm info. So all the rows, first column, and we'll just look at the number of total number of elements, right? So so now we have got all of these. So let us just comment this out. So we are still using quadratics. So no, we are using linear elements. So let's just put line q and make it a quadratic. Okay, so now we'll read the quadratic mesh, and so this is tuned for quadratics. If we wanted linear, we can just make this 2 2. That's all. We just have to make that change, and we have to change our shape functions as well. So Okay, so now that we have done that, I hope we have everything ready. So now let's just change our shape functions. Right, and now we also need to modify our boundary conditions. So let us define I node is the inner node, so that is just boundary info dot, so it is flag 2, I guess. Yes, it is this node which is basically flag 2. So let us just say I node is equal to boundary info dot flag 2, and O node is equal to boundary info dot flag 3, right? So so this will just extract the node which we want, and now we'll just put I node here. And this is our Robin boundary on the outer side, so we'll just put O node. Right, so I think that's about it. I think we don't really have to make any other changes. If there are any changes to be made, I think we'll just get an error. So let's try to run this. Okay, I just have to set the order as 2. Alright, so I guess I just have to do a transpose here, I guess. Okay, so now we have got our solution, I guess. No, we haven't got the solution. So am I defining this correctly? Okay, so there is some issue here. The number of elements cannot be 1. So I just missed this guy here. Right, so now we are getting the solution, and so this analytical solution appears like this because we just went from node 1. So the node ordering was scrambled. So we went from node 1 directly to node 2 here, right? So the analytical solution is just showing that it's just appearing scrambled because we have used that straight line representation. So let's just change that. Yeah, let's put this as cross. Right, so now you are seeing the fit is really good between the analytical and the gmesh based solution, right? And then you can just do the error analysis just as before. So this is for a quadratic mesh, and you could also do this for a linear element or a cubic element. So really the process is the same, and you can see that really we just changed the shape functions. We aligned the shape functions as per the nodes of gmesh, and we just plugged in the node and element connectivity list from by reading this gmesh script. And we just added also a boundary info so that we know the inner and outer nodes. So this is a very simple process, and hope this was really easy to follow. And now really since we have solved it in 1D, now we can go to a 2D problem and eventually to a 3D problem, and you can see that we can just go adding layers onto the same solver, and it is very easy. And most of the changes are again just in the boundary conditions, in the shape functions, and in the mesh. Okay, everything else is almost the same. Okay, so this is the power of finite elements, and in finite volumes you will not be able to crank up the order of elements or go from 1D to 2D to 3D so straightforwardly, but in finite elements you can do it very easily. It can handle curved boundaries also very well. So let's go step by step. So next we'll look at now the 2D problems and then the 3D problems. So I hope this was useful, and I'll see you again. Thank you.